My name is Dr. Eyal Weiss. I'm the founder and CTO of Cybord. My background is in electronics, mechanics, and mechanical engineering. I have 28 years experience in the industry, in research and development. All right. Well, the main message that I want to bring in this talk is that looking at components gives you all the information you need. So actually knowing the components you use is the key to deliver high quality products. This is because 8 out of 10 times failure in electronics is actually caused by the components themselves, the electronic components, not the assembly, not the process, not the testing, but actually the components themselves. And if you look at your components, you can get the best value. Problem is that until now it was impossible to look at all the components, but today with AI technology and big data, it becomes possible. And while you're looking at the components, you can reduce the recalls or any quality related aspects. If you only use components that you verified by seeing them using AI, you can get great quality and traceability that is based on evidence, that is based on what you see, not on any other parameters, any paperwork, just what you see. There's a problem in the supply chain, nothing new, but it's affecting everything. It's affecting, there's a shortage in components, affecting the KPIs, and it allows low quality products and counterfeit products to infiltrate what was safer before, to infiltrate the production lines. The big shortage is forcing people to buy from different sources, and the sources are just collecting whatever they can. So this is becoming more problematic than ever. The unsafe components may be either fraudulent, problems with components that it could be. Fraudulent components are basically counterfeit or things that are designed as a fraud to make money, not for you, but for the fraudulent person. So they can be either recycled components or fakes, which is just a copy. Component with forged age, that is a component that was, let's say, a reel of 10 years old that you only change the label and make it new and sell it for a top dollar price. It could be cloned or copied and so on. So all this is kind of fraudulent components that are out there in the market. Another issue is the quality. Quality is also connected to fraud, but not only. You can see you have defects even in good suppliers and sources. It could be done just maybe because this is the statistics, and it could be also because of bad handling of storage or bad luck, and oxidized leads, which is corrosion on the soldering leads. All this is of course more pronounced in today because there's exposure to lower quality components. And the next thing is bad information. You don't always get the right information with the components that you buy. Sometimes you have undocumented lots. You have in the same reel few production lots that are not documented. There's errors in production lots or in date codes, and there's partial data. For example, if you buy components from brokers, very often you don't see the lot codes because they are erased. So all these are examples of bad components, but these are actually, what it means is that today traceability are actually incomplete because data source is partial. Where do you get the information for traceability? You get it from the documents that you get from who you buy the components from. So you get partial information. When you take it into your system, you take only a part of it by either typing or using a bar scanner or scanning codes. It's prone to human errors and it's low details. It's only very few details are being absorbed into the system and they are not visual verified. So you just get a paper and you trust what's written on the paper, assuming you didn't make any error while you're copying the paper. Our solution is very simple. What we're saying is trust what you see. Don't trust anything else. So you can get quality and traceability based on evidence, based on what you see. We're working to get there by looking at the components at the three different stages in the production. we're only using software. There's no hardware involved here, only software that is used to get information about the components, understand what it is, and trace it, saves it for quality use later. So what's the technology behind this? The technology is based on images that we're using. For example, we can identify a label by taking a picture of the label of the reel or whatever, and then you can automatically detect everything that's written. It's not just OCR, it's understanding what we read. We understand that this part is the part number, this part is the quantity, date code, and so on, regardless of the manufacturer of the reel or the source, or is it a reel coming from a distributor or whatever. So the idea is to use NLP technology to make this robust identity labeling. So you don't trust anything. There's no manual entry of data. You just take all the picture of the entire reel with all the labels on it, and then you can decode it using AI. We can also identify the parts themselves that are being placed on the components based on how they look. And the interesting thing is to look for homogeneity. If you're looking at all the components that you're placing on a production line on a board, then you can see that if all the components that are coming from the same reel are the same. For example, you can see that these two groups came from the same reel. You see that they are not looking the same, and you can see the distribution of the dimensions that are also not the same. So there are two different populations inside the same reel. So this is something that you want to know about. The most powerful tool, which is relevant for traceability, is being able to tell who is the manufacturer of the component, not based on the documents, but based on the component, the picture of the component. You can see here that, for example, this is a Murata capacitor and this is a Yageo capacitor. They look almost the same, but you can see that they are different. Now, you can see it with your eyes, so it means that if you train a machine to do that, they will be able to tell the difference between Yageo and Murata. And we have a database of over 2 billion components already analyzed, so the AI capability of being able to tell them apart is exceeding 99.8%, which is really high. Another interesting thing that you can do if you look at your components is to estimate their age, because age can be influenced, or the apparent age of a component can be influenced by the way it was handled, or fraud, or just errors. And you can see how do we do that? We're looking the same way you're looking at the person, and you see by the texture of his face what is his age. Obviously, the young is nice and smooth, and the older you get more creases. So there's a roughness changing also to the soldering leads of the electronic components. This is because there's a corrosion layer that's getting thicker and thicker with time, and this is causing the texture of the surface to be rougher, and it reflects light differently. So we can estimate the age of a component based on how the light is reflected from the soldering leads. So this gives us a good estimation or if it is a good component to use, or is it bad? Is it really new as it was reported in the traceability papers? Another interesting thing you can do is look for defects. You can see you can find cracked components, all kind of defects on the body of the components just by looking at them. Of course, this is relatively rare, but surprisingly, we did a research on over 20 million components, and we found that there's about between 60 and 100 parts per million of defects, which is a lot more than people think about components. Now, the last interesting thing I want to tell you about when you look in the components is you can read what it says on the component. Now, that's not just OCR. You can take a picture of the component from the top side and understand what this means. So based on the marking, I can tell you what is the part number, what is the manufacturer, and what is the lot code and date code. and we can cross-reference it with information we get in the incoming data and in the SMT machines. So the idea is to be able to decode not just the text, but what it means. Give me a picture of a component, and I will tell you part number, date code, lot code, regardless of what component it is. This is, again, using the power of AI and big data. So that's all basically the technology tools that we use on every individual component going on every individual board. Let me show you a quick video so we can see how it works for traceability.
8 out of 10 times, failure is the component fault, not the production fault. Traceability systems help reduce the recall. The problem is that traceability is incomplete. Partial data, manual entry, human error, low details. In addition, there is no visual verification of the data, and errors and deviations are not always tracked. Let's have a look at how advanced AI can take this to a new level. The starting point is a faulty board. Enter the failure data by board or by component. Find all involved boards. Select the suspect component from the list. You can also use the component's markings as identification. Here is a list of the entire involved boards. That's a big loss. Let's see how forensic AI traceability can minimize it. Run AI forensic filtering. This saves a lot of unnecessary recalls. Reduce the recall. Return faulty boards by evidence. Let's see how it plays in production. Labels are very different. Cybord uses AI for decoding the context. A unique ID for every reel is created. All logistical evidence is extracted. The reel's data is used throughout the process. The reels are prepared for the placement process. This setup is cross-checked with the reel's evidence. During placement, the image of each component is taken. We know from what reel it came to what board it was mounted, and the location on the board. Every component image is analyzed, verifying the reel content. The final station is the Automatic Optical Inspection, AOI. All the components' top markings are captured and decoded. AI Content Identification, NLP Robust Context Extraction. The unique ID for every reel is cross-checked. All logistical evidence is put to use. All data is integrated. It is based on evidence, very detailed, surgical precision. Ultimate control on the components, which makes it a truly reliable product.
Oops, sorry. There we go. All right. So how do we do it? We are software. We don't have any hardware in the system. So the idea is to look at all the components using the already in place cameras. For example, for this first stage, we do AI smart integration for the registration of the material. So every board, or every reel that is or tray that's being accepted, you take pictures of the labels from the top side, automatically collect all the information and storing it. So it's completely automated and there's no man in the process. The next step is very interesting. What we do is we're taking the pictures from the pick and place machine during the placement process. The pick and place machine is picking up component, taking a picture from the bottom side, and then it's placing it on the board. So we see every component right at the time that's being assembled. We already have a protocol with the Fuji, ASM, and Universal manufacturers of pick and place machines, where they built an application specially for us, exporting the images and allowing us to use the images in real time. So for every component during the pick and place, we can tell from which reel it came, we can see it, and we can say to what board it went and the place on a specific board. So using this information, we can really in real time know what component went on which board. So this is really the highest level of traceability, because you can see every component that was placed on every place, and every one of those components was analyzed during doing all the tests that you saw before. The next place that we are installed is in the AUI machine. The AUI machine is taking pictures from the top side of the component of the entire board, while the AUI machine is looking for problems in the placement or in the process. We are looking at the components. We're seeing that is it really the component that was supposed to be there, not was documented, and we can decode the marking on the top side of the component and understand what it is. So if you want to have traceability, not based on the documents, but based on what you actually placed on the board, you can see it. So if you, for example, there were two different lot codes on the same reel, but it was not documented anywhere, or there was an error somewhere along the line, you can actually see each one that was placed. So you can have traceability based on what was actually placed, based on evidence. We're the first to actually comply with the new IPC standard, the 7082A for class B and C. You get the highest level of traceability and counterfeit avoidance with no additional hardware. Now, let's go into details a little bit here. This is the standard as it is today, the conventional way of doing stuff. So for traceability level 1, for example, you have to only know the part numbers that you are placing on an entire work order. So there's no real traceability here. The second level is you know a unique package ID on a reel, and you know to which work order it went. So that's also not really traceability, but it's a low level traceability. 3 and 4 are the really interesting one, because 3 and 4 means that you know which packaging unit, from which reel, and there's a serial number on the board, so you know to which serial number it went. And the counterfeit avoidance that you have, or meaning how sure are you that you're really using the components that you think you're using, is used using sampling testing. Sample testing is meaning that if you bought the component from a broker or from an unauthorized or less authorized distributor, then you have to send the reel to a lab test. But if you don't, if you bought it from an authorized distributor, you don't have to do any testing or any inspection. So that's the level you needed in number 3 and 4 of traceability level. The difference between 3 and 4 is in level 4, you can also know the reference, the designation of the components that are being placed on the board. So it's coming from the same reel, it can go to 2 different locations, so you are separating them. So that's the conventional way of doing traceability. The new standard by the IPC is actually giving you 2 to 4A higher level. This is called individual component. What it means is we don't just know what reel it came from, but we actually see every component going on every board. And we see the component and we can group it to different groups. For example, according to the age of the soldering leads, we can group it to defects group, to dimensions group, or to quality groups, and so on. And this gives you a much tighter control of what you placed on which board. And of course, we know to which board it went and what's the reference designation. Everything is 100% automation, and the counterfeit avoidance is 100% of the components. We don't just sample. Every component that is going on every board is being authenticated. So you're sure that this component is the one that was supposed to be there, not based on documents, but based on what you see. And all this happens in real time. So it's really an industry tool using AI to enhance the capability of traceability. These are the standards involving this procedure. Just a quick recap. So the idea is to minimal recall cost, or a recall can be local recall within the manufacturing ground or external, because you don't have to recall to do a rework or redo the entire batch. You can do it only to the ones that you saw that have a specific problem, so we can only recall and fix them. You can watch and analyze all the components that you use, and you can make smart decision based on evidence, based on what you see, and not based on paperwork. There's no human in the loop, and you get a surgical level of traceability.